Okay, welcome everyone to my continuation of what are my favorite theorems, like my very biased collection, of course. Just keep that in mind. Very biased collection, one of my favorite theorems. Not what are your favorite theorems, maybe they're your favorite theorems as well. But anyway, and I would like to talk about something that I learned quite recently, and I think it's pretty cool. So yeah, we'll go there. But it was one of these problems when you somehow do it by hand, it looks like really difficult. And then it turns out that there's an algorithm which is like ridiculously smart and efficient at the same time. So I would like to talk about what is the complexity of embeddings, or well, embedding is a fancy word of how difficult is drawing. Actually, how difficult is drawing? Kind of a catchy phrase. Catchy, I don't know. But let's have a look in how difficult is drawing. So that's how at least I like to think about it. And by drawing really mean graphs, right? So that's the only thing I can draw anyway. So let's draw all the graphs. And drawing here means planar, whether they are planar. So whether I can draw them in the plane without intersecting. So here, let me draw, here's a graph which I can draw without intersecting. Kind of a very boring graph, I guess. But anyway, here's another graph that gets a bit subtle. So this graph clearly has an intersection in the middle, but I can draw it without an intersection if I'm just a little bit smarter and redirect one of the edges. So instead of doing the second one in the middle, I just do it on the outside. So given an abstract graph, you kind of need to decide whether there's some drawing that is works without intersections. And that always looked to me like a really difficult problem. So if you play around with K5, for example, here, and this drawing is not planar, but who tells you that any drawing, you need to make sure that no drawing is planar. So maybe you could try to redirect first this edge, okay, then you already get rid of two intersections. Maybe then you can, maybe this is a better color, maybe then you can redirect this edge, and then you still have this intersection. You kind of, you somehow play around with it, and you kind of try to make it, to make a planar drawing. Eventually you will convince yourself that it is not possible, but it gets very delicate. And if you have a really large graph, it appears like a really large and a bit sparse graph. These are the very difficult ones. It appears like sparse in the sense of not too many edges. It appears like it's impossible to check whether you can actually do this or not. So how efficient can you do this? And it wasn't even clear to me that there is a nice algorithm to do it. But how to do this? Even for those easy examples, it's usually not completely trivial to see whether you can draw them or not. Because again, this is a question of, I show you a picture, but there might be different drawings of the same picture, like here. And we kind of need to make sure that we are not just too stupid. Well, I'm just not too stupid. You're clearly not stupid, but I'm too stupid to find the correct drawing, right? So it's kind of a really tricky thing. How to do this? You need to go over all drawings, and there are, of course, like millions and trillions and infinitely many drawings, obviously, billions and trillions of drawings, yeah. So it's kind of really, really difficult and not so clear how to do this. So that's why I find the result in the end like super, super beautiful. Okay, so can we do this? Can we check somewhat and maybe efficiently, maybe even with a machine? And if you want to pause the video and open your favorite computer algebra system, it will have something that is called isPlanar, some version of isPlanar. So actually there is an algorithm that is efficiently implemented. And I'm essentially talking about this algorithm now. And I say that again, I think that is like really surprising, because to me it looks like this problem is supposed to be like really hard. Anyway, you can ask the same question on any surface. So planar is just, I can draw it in the plane. The plane is maybe not the most exciting surface ever. I could also think of drawing things on the torus. So here the Hewood graph is drawable on the torus, but not on the plane. And kind of like this Hewood graph, because you can somehow see that you can tile the torus with hexagons. You can't do this with a sphere, for example, but you can do it with a torus, because the torus is flat. Yeah. Anyway, and you can see the hexagons in the picture. So it's just, you go around in the minimal way you can go around. It's always a hexagon. 1, 2, 3, 4, 5, 6. The minimal way you go around will always be a hexagon. So here's another one, maybe. Okay, something like this. 1, 2, 3, 4, 5, 6. Perfect. So these are all hexagons, and the hexagons sit nicely in the torus. So you can actually draw them on the torus. And you can also kind of exercise. It's fun exercise. It's actually a fun exercise. You can actually draw K3, 3, and K5 also on a torus. In fact, every graph can be drawn on some surface, some genus. And the way to see this is the following. So say you have some crazy graph, whatever it is, you someone need to get rid of the intersections, and you can just build a little bridge. So what does any street planner do if there's an intersection and they don't like whatever, you can build a bridge or a tunnel. So I can bridge over here, I can bridge over here, and so on. And a bridge is really nothing else than a handle. So putting on enough handles on your little surface, you can kind of get rid of all intersections. Anyway, how efficient can you do that again? So how efficient could you check whether K5 is embeddable in the torus or not? And this now seems to get really insane because like surfaces are not that easy to imagine in some sense. And already the planar one is like, well, it looks like very difficult. And now we're going to higher surfaces. So how on earth is that supposed to work out in any way or form? It's just a bit strange. So how can you do this? It's kind of not so clear at all. Turns out that there's a nice, very nice answer. Kind of complete generalities. It's like ridiculous. It's ridiculous. Anyway, the things that work, kind of, is the following idea. So you can have this idea of forbidden minors for planarity, for example. The graph is planar if and only if it doesn't contain our good old friends from before, this one and this one, as minors, which is kind of easily checkable in some sense. It turns out that this is so for planar, that's kind of okay. So we can write an algorithm that looks for minors, for exactly those as minors. And you can do something similar for other surfaces, but it gets a bit tricky because those lists get really insane. So that turns out to be not quite the right way of doing it. This is kind of abstractly the correct thing to do if you want, and it gives you already a very efficient algorithm. I will comment on that in a second, but you can somewhat even do better without knowing this forbidden list. It's like, I mean, that's like insane. So I know the statement about planarity in K3 into K5 for a long time. It's called the Kuratowski-Wagner theorem. It's one of my favorites. It's kind of well known. And my first thought on this was like, oh yeah, that's what you should do. And then I also thought, yeah, maybe checking for minors is not super efficient, but it's at least an algorithm, right? At least an algorithm that gets you there. And it turns out that it's not the correct, whatever that means, way of doing that. And there's a better way of doing that, which is kind of beyond this video. It's a bit tricky, but the link to the paper is certainly in the description. And it really turns out you can do this like in a ridiculously fast way, namely in linear time. So in O of n, if you like, that notation where n is the number of vertices. So n is just the number of vertices. And this is ridiculous. I mean, for planar, it's already ridiculous. But for every surface, you can do that for every surface. There exists some constant such you can check it in linear time. Okay, and it's even better. It finds the embedding, right? It's not that just checking, it not just gives you yes or no, but it finds the embedding. Or if it doesn't embed, it gives you a list of minimal subgraphs, kind of the forbidden ones. It gives you the list of the forbidden ones. So if it's true, it finds for you the embedding, and if it's false, it finds for you the obstruction. And that all of that in linear time. And you're just like, what on earth is going on here? This is just ridiculous, okay? So to try to do this by hand, try to show that a graph is planar by hand, and it gets completely insane. You get completely lost, or at least I get completely lost. And then there's this algorithm, which is ridiculously fast, which works in linear time for every surface. And it does more than it just finds the embedding or the obstruction. And this is kind of fantastic. So if you ever wonder how to find this list of potential obstructions here that I mentioned here as a problem for higher genus, you could run this algorithm actually, and eventually you will find this list of forbidden minors. So it's an absolutely breakthrough in, let's say, geometric topology, if you want. Just this algorithm is just absolutely, or topological graph theory, whatever you want to call it. It's just absolutely fantastic, right? So for planarity, I think this is already mind-blowing, but it works for arbitrary surface in linear time. It's just one of my favorites. And I just learned that recently. It's just absolutely beautiful. Linear time. Can you imagine that? Linear time? Anyway. And this is kind of weird, right? So checking embeddability on a fixed surface is like super easy. Now, let me call that super easy. Let me call linear time super easy. Kind of the opposite problem, finding the minimal surface, like you would think, okay, checking embeddability on a fixed surface, so it's kind of easy. Finding the minimal surface should also be kind of easy, right? Turns out that is an NP-complete problem. It kind of does exactly the opposite. So that's an NP-complete problem. And this whole problem somehow walks along the border. It's kind of really strange. So checking for a fixed is linear, like as fast as it gets, and checking, kind of finding the minimal is still NP-complete. And essentially what happens is the following. I haven't found a very precise statement, but let's just say our little algorithm runs in something with n, yeah, O of something with n. N is the number of vertices. Let me make some space here. And I think then there is actually a 2 to the g in front, where g is the genus of the fixed surface, which if you just g fixed, this is just a number, so you don't really care, and the complexity won't blow up. But if you're now varying g, then your leading term is actually an exponential, and that's where this funny difference between NP complete and linear actually comes from. This is not quite true, I think. I haven't found a very precise statement, but this is roughly how the algorithm looks like. So this kind of strange behavior here is explainable by, okay, it's linear in n, but it's actually exponential in the genes, right? So that's where that comes from. Anyway, the algorithm is still, as I haven't explained, it is a bit too much. I think it's not so bad, and actually it's implemented in most computer algebra systems that I know. It is implemented in Magma, for example. If you want to check whether a graph is planar in Magma, it will run one-dimensional algorithm, but it kind of was too much to press it into a video. But it's somewhat linked in the description. And it's like really fantastic. Let me repeat that, because I think planarity looks like a very difficult question, but then it's solvable in linear time, and even better, it gives you the embedding, it gives you the abstractions, whatever. It's just absolutely ridiculous. Anyway, I hope you enjoyed this video, and I also hope to see you next time.